Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Nuclear power is the largest source of low-carbon energy in the U.S. and Europe. Its potential to provide a clean, steady, and increasing baseload is currently unmatched. However, traditional nuclear power plants are extremely expensive and they become nearly impossible to build. In this episode, I'm talking with Eric Williams, Senior Vice President and Design Authority at TerraPower, about how the company is rewriting the future of nuclear power. Eric oversees the engineering associated with TerraPower's Natrium Advanced Reactor. He has 25 years of experience in the commercial nuclear industry, and he has spent the last 15 years developing nuclear power plant designs with an emphasis on safety. He holds a Bachelor's of Science in Mechanical Engineering from the University of Florida, a Master's of Business Administration from the University of Lynchburg, and a professional engineering license. Eric, thanks for taking the time to talk with me today. Let's jump right into this.
All right, great. I'm very happy to be here.
I'm really excited for this episode. Will you tell us a little bit about TerraPower and its history and its mission?
Yeah, maybe the way to begin is I'll tell you what the mission statement is for TerraPower today, and then a little bit about the history and how we got to that mission statement, because it wasn't encapsulated that way when the company first began. So the mission statement for TerraPower is to solve the world's toughest problems in energy, climate change, and human health through innovative nuclear technology. But we didn't get there right off the bat. It really began as the way a lot of startups do, as an idea in someone's brain. And in this case, it was the brain of Bill Gates, who's currently the chairman of our board. There's actually a great documentary that came out in 2019 called Bill's Brain. That's really interesting to check out. And it talks about, one of his three major concerns being climate change. And that's really where TerraPower kind of fits in. And it really began back in 2006 when he was interested in trying to accelerate our solutions to the climate change problem. And he wanted an investigation into, what sort of technologies were out there. Were there any technologies that maybe were laying dormant that, if some innovation were to be put on the problem, we could potentially bring up a new solution to the climate change problem. It didn't presuppose that the solution would be nuclear. So it looked at all kinds of types of electricity production, knew it had to be carbon free to make a difference, and it had to be at a scale that would make a difference as well. And so he got some of his technical advisors on his team together to go out and look at what was available in the world. And when they did that, they came across a couple of very interesting concepts that were in fact lying dormant in the nuclear space. And one of those began here in Washington State through the, you might know the Fast Flux Test Facility out in Richland, Washington, which was a type of reactor called a sodium fast reactor. That project was halted a while ago, back in the early 1990s, but it was in the middle of developing something very promising, which was the way to add additional safety to nuclear power plants and also additional efficiency and ways to expand the lifetime of the fuel that we put into the plant to actually get as much energy out of it as you possibly can. And that was very promising to him. And he got a team together. And then finally in 2008, they formed the company TerraPower because they said, we really have a concept here that can change the world. And we want to build our company around it and see if we can go commercialize this technology for the world. And so that's how TerraPower began. And, the company started to grow around some materials and testing problems that this technology faced. And so right off the bat, the company knew those were kind of longer term investments that had to be made. So started to form relationships with our national labs here in the US and other key partners to help us develop that technology. So the company really started to grow. Once the business plan started to form around this new type of nuclear reactor, then the question was, where do we need to go deploy this? Where is the market for new nuclear? And at the time, it's kind of interesting to think back that the market really wasn't the United States at the time. There was really not much going on in terms of nuclear innovation here. And so the company was actually looking outside the U.S. And if you really want to make a big impact on climate change, then at the time there was no better place to go look than China. So actually, our first market that we were deploying to was going to be in China because they had all this coal power in China that they were trying to transition away from. And they were also growing very rapidly and had still a large demand for additional electricity production. So originally, we talked with the U.S. government about going to China, and they really encouraged us to, because this type of nuclear power is actually also proliferation resistant, because the fuel stays in the reactor so long and you're not taking it out to do any additional reprocessing with it. It's actually a very proliferation resistant technology, and they wanted us working with China at the time. So we made special arrangements to go do that. And that's where everything was headed up until 2019, when everything really pivoted fast, because the government looked at what was happening in China with technology transfers, and they said, okay, that's it. We're no longer going to be exporting advanced nuclear technology. And so the company had to do a total pivot back to the U.S., which was now becoming a really great market to deploy nuclear energy. So a lot can change in 10 years or so. And so that was, in my opinion, very much a success story for the company, because the U.S. supply chain has the potential to grow, and we have the chance to really improve life here, in the lives of our communities. So I was really happy that we got a chance to do that. And that led in 2020 to us making an application to the Department of Energy for a grant to do a demonstration reactor. I can talk a little bit more about that later, but that's what led to the Natrium design nuclear power plant that we're deploying in Kemmerer, Wyoming. And so, things are going really great for the company. We've got this great product that we're demonstrating. And along the way, there have been other innovations that kind of spawned off of this one main line to develop the Natrium reactor. We also have a second reactor design called the molten chloride fast reactor that needs more development to reach its demonstration phase, but also has a lot more promise for nuclear technology development. So we're also developing that. And we also have a medical isotopes program that also grew out of the work we were doing on nuclear power plants. So now the company is really beyond its, startup phase. I think it's really growing quickly. We have about 600 employees, and we have 3 really promising product lines that we're developing.
Every time I talk to anybody in the electric power industry, right, we talk about, non-carbon emitting, reliable, dispatchable resources. What does that look like for us? Certainly as a nation, we talk about the world also. And I think you end up at nuclear. So now the challenge is, how do you go to, when we're a nuclear country, I guess, maybe the best way to say it, to where we're at today. And I think you're going to have to use gas or something like that to bridge us. Well, there's a place, I think, for, all options, whether it's solar or wind or something. They're not certainly as reliable as those 2 sources. And, it's really hot here in Pullman, Washington today at 100 degrees. We really like having dispatchable power, because what I also notice is it gets really, really hot when there's like an inversion and the wind doesn't blow out here. So that we need that. So we end up at nuclear, which is really good. And I've been a nuclear fan forever. My dad was in the nuclear Navy. I've grown up around this stuff. I've worked on nuclear submarines. So I know it can be done safely. So I think we just take that. We'll talk about safety, I think, in a little bit. But why your Natrium design versus, a water design or SMRs, small modular reactors? How did you guys end up where you're at with this particular technology? What problems was it solving that weren't already being addressed with the present state of nuclear reactors?
Yeah, that's a good question. So, my history is I used to work a lot on the current fleet of light water reactors that we have in this country. So I spent a lot of my career working on the existing fleet, and then I started to work on new light water reactors. So, an incremental innovation from the current fleet. And now I'm working on these, we call them advanced reactors, which the main difference is we're not using water as a coolant. Typically, we're using some non-water coolant, such as liquid metal in the case of a sodium fast reactor, or it could be a high temperature gas, or it could be a molten salt. And so what's different about it is the ability to get out of having to have a high pressure system. I think the current fleet of light water reactors that we have are really being held back by that. There's really, you can only take them so far. You can keep innovating, you can make small improvements to them. Reactor designers have definitely made improvements to safety over the years, like the plants we just built in Georgia, the AP1000s.
Oh, yeah.
Those have made, really good improvements in safety, going from active safety systems that require electrical power to operate or operator actions to operate, and moving them to passive safety has made a big improvement. But you still have a high pressure system, and that high pressure system, stores energy that has to be released in order to get the cooling to the core. And so they're just always going to be held back by that. And so the advanced reactors, such as natrium, have gone to coolants that can be at very high temperatures and remain liquid and be well below boiling point without needing to apply high pressure. And that has been the real game changer for everything, for safety, being able to have a much safer system because you don't have all that stored energy. And also being able to achieve cost improvements, because really, we can talk about this more, but the real enemy of advanced nuclear power is cost. It's really getting these plants into an economic phase where they can be deployed widely and people are really demanding them. Those have been the real game changers for advanced reactors and how they're different from existing reactors.
So sodium reactors have been, I was doing a little bit of research on maybe in the 60s, maybe a little bit later than that. So we've tried it before. Why the resurgence now? What's different than it was, say, 20, 30, 40 years ago?
Yeah, that's a good one too. There was the great thing about it is there was multiple decades of research done here in the United States and also around the world. There's still research going on around the world, but it all really came to a halt or a pause in the U.S. back in the early 1990s. They were doing tremendous experiments with the experimental breeder reactor 2, which was at Idaho National Lab, and the FFTF fast flux test facility in the Tri-Cities. And they were testing and demonstrating the safety characteristics of these plants and really trying to investigate a more advanced type of fuel, moving to a metallic fuel from an oxide fuel design. And so that's really where it all came to a pause in the early 90s due to a couple of reasons. Really, the world discovered that uranium was not as scarce as we thought it was. The world really, back in that time, believed uranium was going to run out, and that, nuclear power was this too cheap to meter form of energy. We were going to use a lot of it, and we were going to run out of uranium. And so the type of reactor that they were developing is a type called a breeder reactor that can actually, breed fuel while it's operating more than it's actually burning. And so it was this tremendous opportunity to address that scarcity of uranium that we thought we had. Well, it turns out that we discovered enormous reserves of uranium here in the United States. There's technology that we think is available to extract uranium from seawater, a very plentiful source out there. So the world turned away from having to be very tight with our fuel and develop this new type of reactor, which needed some development. So there was some costs associated with it. And so then it just turned back to light water reactor, a proven technology already in use in nuclear submarines and commercial nuclear power plants. Everything is running well. We can do that later. There's no rush to develop the breeder reactor. And so it was kind of put on pause. And what TerraPower did actually is go pick up where they left off. In fact, we went back and gathered fuel that was irradiated back then, but never opened up and tested to get the data out of it. And we've actually recovered that fuel, sent it to the national labs, had the data collected and processed, and are actually using it to qualify the fuel that's going into the natrium reactor. So none of that was wasted, which is the good thing.
That's really cool.
All that data was there, and we're making good use of it.
Well, let's move on to the reactor that you guys have under development. So recently you started building the first natrium reactor in Wyoming. Why there? And will you tell us a little bit about the project?
Yeah, Kemmerer is actually a beautiful area of Wyoming, very small community. We like to joke that the elevation is larger than the population because it's at about 7,000 feet elevation out there, but extremely flat with beautiful mountains, and population's only about 1,000. So it's a very small community, not too far from Jackson Hole, Wyoming, in fact. So that's the location, and I can talk a little bit about why there. But first, maybe just mention, what is natrium? Natrium is this sodium fast reactor type. And there's some innovations that we've made to it. And one of them is that it also has an attached molten salt thermal energy storage system that sits between the nuclear reactor and the balance of plant that's generating steam to generate electricity. So that's what natrium is. That means that it can generate 345 megawatts of electricity all the time, constant, 24/7. And then it has, through this energy storage system, the ability to ramp up to 500 megawatts electricity for smaller periods of time, like 5 hours. But it can do that multiple times a day, every day, going up and down to 500 megawatts electric, down to 100 megawatts electric, or sitting there at steady state, 345 megawatts electric. So Eric, it is this unique product.
Yeah, let's pause real quick. Maybe expand just a little bit on it to folks that are listening and explain, because this is my takeaway when I was taking a look at your system. Is you've got, I think you said 345 kW, right? Is the output. So let's say you really have a system that needs more than that, and what the way I looked at it is, you're not putting out the max power you need, like a gigawatt or something like that. You're just always putting out 345. And what you have is this essentially a salt battery out there. So the demand is only 200 kW, you're just storing up the battery, right? Just keep putting out that 345 to ramp up the battery. And then, I come home at night and my kids are watching TV and I'm cooking dinner. My wife's doing, where we need a lot. So then I can suck out of this battery. So it's a really clever system. It's not just what you guys are talking about here as a nuclear reactor that's just kind of providing, hopefully, for baseload or something like that. But it's also got a peaking station in it too. And what's pretty clever is you separated the two. It's not all in I call it the inside the nuclear fence, right? The battery is outside. And I think one of your points was you can really reduce costs if you can use commercial off-the-shelf parts and products versus having to make everything nuclear grade.
Mm-hmm. That's exactly right, David. You've done your homework. Good job.
Oh man, good.
Yeah. That's the exciting part of this. That's actually never been done before, is to actually generate electricity with a nuclear power plant that allows the grid operator to dispatch the electricity without having to change the nuclear island or go to the nuclear operator for anything. So the nuclear island just sits there cranking out 345 megawatts electric all the time. That never changes. You load follow with the energy island, what we call the energy island, which is where you're storing that energy in the form of molten salt. So we're not talking about electrical batteries here. We're talking about think of two large tanks. One of them has hot salt and one of them has cold salt. And if you want to generate more electricity, you just flow more of the hot salt to the steam generator to crank out more steam to the turbine. And that draws down the level in the hot salt tank. And to a point when about 5 hours into that, you have to stop that and actually recharge that tank. But for 5 hours, you can go up to 500 megawatts electric if the grid demands it. Like you're saying, when wind and solar kind of die off in the evenings, or maybe it's, in the morning time when people are waking up and they haven't cranked up yet, you've got that ability to fast ramp up and down to meet the demands of the grid without changing anything that the reactor is doing.
That's
so the
amazing.
Reactor can just operate safe and sound and never have to go through those transients that actually would, take away from its lifetime over time. So,
and I'm no nuclear reactor kind of guy, but my understanding is you turn a reactor on, you run it at one output, and that's all. You never want to cycle it up and down, right? It just wants to go at one particular set point. So in let's call it the renewable side of the electric generation, obviously they all recognize the sun doesn't always shine and the wind doesn't always blow. So their answer to the battery is lithium ion batteries that are picked megawatt, 4 megawatt, and they're usually rated in about 4 hour increments or something like that, which compared to what you're talking about is nothing, right?
Yeah.
It is tiny. Why isn't everybody jumping up and down on this idea? It's almost too good to be true. How come we're not doing this everywhere? Every time we decommission a coal plant, why wouldn't we drop one of these things in here? Because the infrastructure is already there, and it seems like the perfect place for putting a nuclear reactor, the system you're talking about here.
Yeah, well, actually, coal to nuclear transition is actually a big topic in the nuclear industry. And it's one of the areas that, we see a lot of growth. And in fact, that is a big part of why Natrium is deploying in Kemmerer, Wyoming. It's because of the Naughton coal plant in Kemmerer, Wyoming, is going to be retiring. And the Natrium plant is essentially coming in and replacing an equivalent amount of electrical output that they're losing from the Naughton plant, picking up the same water rights that the Naughton plant used, using the same grid connections that Naughton plant used, and a lot of the other infrastructure and the nearby land. So there's a lot of benefits to actually going in and replacing coal to nuclear. But why isn't everybody using it? There are other aspects to that, like renewable plants actually do use thermal energy storage. The large concentrated solar plants use the exact same design of thermal energy storage that Natrium uses. In fact, it was our purpose to use the industry standard type of thermal energy storage so we wouldn't have to invent something new. The new thing is attaching it to a nuclear plant because renewables use the energy storage for the opposite reason. They have an intermittent source of energy generation coming from renewables, and they use the energy storage to provide more of a baseload electrical output to address that intermittent energy generation from, say, a solar plant. And Natrium is doing the flip of that. It's actually got a constant energy storage coming from the nuclear island, and it's using it to address the intermittent demand that the grid has due to renewables saturating the grid, so that it can ramp up and down quickly and address changes in the grid. So it's actually the same technology, though. We're adding some reliability to it because nuclear plants are really expected to be up in the 95%, 98% capacity factor range. So we want that energy island to be able to run all the time and never have to go down. So we're adding some reliability, but it is off the shelf. The thing that keeps some other technologies from using this type of energy storage is the fact that it wants to live between about 300 and 500 degrees C. And it just turns out that Natrium has the exact temperature output coming from the reactor that fits well within the range that this molten salt is well characterized and performs very well. If you were too hot, which some other advanced reactors are, they're too hot, they're above 500 degrees C, it causes the salt to decompose into different species, and you can't really use it for thermal energy storage. And if you were too cold, like existing light water reactors and other energy generating assets are too cold, then the salt freezes. So we just happen to be in that sweet spot, which is nice that Mother Nature has favored us in that regard. So we can use this industry standard salt composition that the solar plants are using.
Maybe we touched a little bit on this, and maybe that was the real cool innovation, was with the output of the reactor with the salt temperature. Maybe there's some other innovations I'm missing that you'd like to tell us about, but also maybe then coupling, maybe we talked a little bit too about the safety aspect of it.
Right, exactly. We believe that existing nuclear plants are extremely safe as they are. But when you have that high pressure system, it requires you to take extra measures to make it safe that require extra cost in the capital for the plant. So it's safety and economics that go hand in hand there. But some of the innovations, that the Natrium plant has, in addition to this molten salt energy storage, which is a big one, but just the fuel design, I mentioned that the existing U.S. research or the U.S. research from the 60s, 70s, and 80s, was all moving towards this new type of fuel. And the Natrium has picked that up and innovated a lot further with it, because what we're trying to do is get to the point where the fuel required for a power plant doesn't even need to be enriched in uranium. So you can actually take depleted uranium that you're mining from the ground, and the reactor can burn it so efficiently that it doesn't even need to be enriched. And the waste that comes out the other side of the reactor is very low volume, very low mass, because you've used all the energy you can out of it. Current reactors discharge fuel assemblies from their reactors that still have an enormous amount of energy content that's left to be used. And so it's just a matter of being more efficient with that.
But Eric, isn't it, let's call it the waste fuel, really a function of our policy on reforming or not reforming the fuel? That's something we have chosen to do versus what they do over in France or Germany. Well, they'll reprocess, they'll use every drop they can out of it. And we've made a decision not to do this. That's kind of on us on a policy standpoint, probably.
It is on us. And we're, when we're sitting here at TerraPower and we're thinking about how to deploy our reactors, one of the things is we want to avoid having to have a reprocessing plant, because that's a whole separate plant that has to go work along with the nuclear plant to keep it running and producing electricity. And because we haven't invested in it, it's a whole new technology that still has to be developed to keep the reactor running. And so I think we're the only advanced reactor vendor that is making a fuel that does not require any reprocessing. It can be burned efficiently in the reactor that we have because we're building it for that. We're designing the core in order to function that way. And so that's one of the key innovations. And then with safety, a lot of the safety comes from the fundamental choice of the reactor configuration and some of the choices we made in the architecture of the plant to make it more safe. A lot of it comes just from the fundamental choice of a liquid metal coolant, like we said, that can remain at atmospheric pressure. But even your listeners who aren't engineers, I think, can appreciate that metals can conduct heat very well. You can experience that when you're cooking and you grab the handle of something off of a stove and you burn yourself. And so what we have here is a system that has metal fuel, metal coolant, and it's surrounded by a metal vessel that holds it all together. And so removing heat from this reactor is very efficient, so efficient that we can do it just by blowing air across it. So there's no reasons to bring in water to cool the reactor, which runs out over time, like we saw in some of the other accidents worldwide, like Fukushima. We have this ability to cool the reactor indefinitely with air because it's so efficient at removing heat. So that's one of the key safety features and innovations. And then the way that we've designed it, the actual federal regulations have changed to allow a much more modern, advanced licensing framework that we are using for Natrium and other advanced reactor vendors are too, to get a safer design that's got a smaller footprint for the real nuclear quality grade equipment. Mm-hmm. And so the Natrium reactor really has everything surrounding this vessel that contains the nuclear core and doesn't need to provide any other additional equipment outside of that to provide the safety. So it leads to a very small footprint of that, where you're putting all the cost of the plant. And so those are some of the main innovations. And you mentioned it from your homework. There is this idea that we decoupled that safety grade portion of the plant from the non-safety grade portion of the plant, which provides a lot of safety because there's so much coolant in this reactor that just is always there, that there's no reason to rely upon any of that molten salt storage or steam generators or any of that power electricity producing equipment for safety. Whereas in existing reactors, it is. And in existing reactors, if the turbine trips, the reactor has to trip as well. And in our reactor, the difference between those two events, the turbine trip and the reactor having to do anything, is a very long period of time. So,
yeah, and as I recall in the nuclear industry, right, if you trip off a reactor, there's a lot of questions that have to be answered by people, right? I would not want to be in the hot seat for that one. One of the questions I had is why build new nuclear instead of focusing on adding more renewables? And after our short conversation right now, I'm going to change my question, if I can, to why would I ever want to buy or build renewables when I could build one of these reactors? They seem like they work at scale. They take up a lot less space. We've already got trained people that can operate these things at I'll call it grid scale or utility scale. It's like,
Yeah. Well, I do think that they both work together. During the daytime when the sun is shining and, the wind is blowing and you have essentially a a way of generating electricity from a free source of fuel that nature gives to you, why not? It's a great way to leverage that source of electricity. But what Natrium does with the energy storage component is it works well. It complements the renewables. So I think they both kind of do work hand in hand, because to use that energy storage, you actually have to be able to bring the electricity production down. So you want the renewables to be functioning full time during the daytime, and you want to bring Natrium down to lower electricity output of 100 megawatts, let's just say, so you can recharge those thermal energy storage tanks and get ready for the evening when your renewables are going to come down and you're going to crank it up. So the two really complement one another. And I would say that the big reason for looking at nuclear that a lot of people don't appreciate is the energy density of this type of technology. It is incredible. It's mind-blowing how much energy exists in such a small volume of fuel, which then leads to a small footprint of the reactor that's generating this enormous amount of electricity for you 24/7. So that's the real benefit of it. And renewables are the opposite. If you think of the latest large solar plant that just went online in California, it was the size of 2 Natriums, but it was 4,000 acres of footprint. And the Natrium, even a 2-unit Natrium site, would be 120 acres, let's just say. So, there's a huge difference in the amount of land you have to use because of that energy density. But the two do work well together. I would say, nuclear energy also provides that stability and reliability that you don't have with the renewables. And with the energy storage and the ability for, the grid operator to just dispatch, you've got a flexible option there that really nuclear hasn't been able to provide up until now. So that's a big improvement.
Yeah, we talk a lot on this episode, or on these episodes, about energy density. I'm a big fan of that. A previous episode, we were talking about what perhaps are the ramifications if they remove the 4 dams here on the lower Snake River. And I was talking, I did some quick calculations. How many square miles would you need of solar to replace the output of those 4 dams? And essentially it's the entire city of Anaheim would be required for solar.
Wow.
We're blessed here with hydro, so I could see that hydro and the nuclear energy going well together, because water behind a dam is a super battery, right? I can't think of a better one than that. Mm-hmm. The Biden administration just recently signed an international pledge to triple the world's nuclear energy by 2050. Based on your experience, what can be done to help meet these goals? Or do you think that's even realistic?
Mm-hmm. Yeah, I mean, I'm pretty hopeful on the ability to meet that. I really think, the first thing we have to do is we have to demonstrate these new nuclear reactor designs, TerraPower's design, but also other designs as well, because there's various different types of nuclear solutions here that, fit well for different scenarios. We have like battery sized nuclear reactors now called microreactors. We have high temperature gas reactors that might be really good for heat for industrial applications. We have Natrium that's really good for electricity generation in a renewables based grid. So we need to demonstrate these, because I think what the U.S. government has realized, and so has the world at large, is that we're really not ready to deploy plants as fast as we need to. And there's really a lot that needs to be rebuilt here in the United States if we're going to be part of this growing global demand for nuclear power. So I would say the first thing we really need to do is execute these demonstration reactor programs, such as the Natrium one in Kemmerer, the X Energy plant at Dow Chemical in Texas. All of these designs need to have their first demonstrations, because that's going to show the world that they can be made economical. They can perform well as designed. They can achieve the safety and get licensed by the federal regulator. And the supply chain has to be rebuilt. Back when we were building enormous amounts of plants here in the U.S., we had this whole great infrastructure across the country that came together to build these components and deploy them. And we've lost all of that. So it all is getting rebuilt through these demonstration programs, or at least starting to. And we need to continue that. We actually need to think international about the supply chain too, and be developing a supply chain in Europe, a supply chain in North America, and a supply chain in Asia to capitalize on all the needs for these plants worldwide. And like I said in the early remarks, that the cost reduction is the big thing that we need to deliver on, and that's in the hands of us, the nuclear technology developers, I think, to come up with solutions that reduce cost, being at atmospheric pressure and having a more efficient design and smaller footprint. All these things are really getting at one of the main problems with nuclear power historically is the cost. So if we deliver on that and demonstrate those cost reductions, that's going to make a big improvement. And then it goes without saying that we need to do all this work safely. We're going to have safe designs. And when we actually operate these plants and construct them, even before that, they need to be built very safely at high quality standards. And that's what's really going to make this industry take off and meet that 2050 goal across the world. And I think maybe one last point just on teamwork. I have definitely learned in this job that to do anything in nuclear power, it takes a team. It takes your suppliers. It takes the nuclear vendor. It takes the regulator. It takes universities and national labs and a whole network of partners that have to all work together. And if everybody's just trying to hide their proprietary data from everybody else, it really makes that hard. But when we work together, we can do these big, complicated things.
Maybe pivoting just a little bit, TerraPower also has a business arm focused on isotopes. What are you doing in that area?
Oh, yeah, this is a great story. It's kind of a story within the larger TerraPower story, but this is an exciting development. It actually came from when we worked on our molten salt reactor, just a totally different type of nuclear reactor. One of the things you have to do is you have to build a team of radiochemists. Think of regular chemists that are also working with material that's going through radioactive decay chains. And so we built a radiochemistry lab. We started working on making the fuel for this other type of nuclear reactor. And those radiochemists are those people who realized that there was this opportunity to develop a new type of medical isotope that could really revolutionize the way that cancer is treated. And so they brought that to the TerraPower board, and it was such a big opportunity. Even though it's not really in line with a power reactor design, it's kind of an offshoot of it, and it was something we had to pursue. So really, there's a long history of medical isotopes from the nuclear industry, both for monitoring for cancer as well as treating cancer. But what we know about this, and if you've ever had family members that went through radiation treatment, is that unfortunately the type of radiation treatment that's been used to date comes with a lot of collateral damage to healthy tissue. But there was a study back in 2016 on a new type of treatment called targeted alpha therapy that actually was remarkable in how effective it was at treating certain types of cancer and how little collateral damage it had, because there's multiple different types of radioactive decay. And this one is something called alpha particle decay, which means that the radiation is affecting a very small distance from the radioactive particle, actually less than the diameter of a human hair. And so it actually is able to target just the tumor and not affect the healthy tissue around it, which is amazing. And so TerraPower found out that, this is a swords to plowshares kind of story, that there's this stockpile of material out at Oak Ridge National Lab. It's uranium-233, an isotope of uranium that was made during the Cold War as an experiment. They determined they didn't want to use U-233 very much. So there's this huge stockpile of it sitting there. And over time, this U-233 goes through natural decay to thorium-229. And what our team realized is that the thorium-229 could be used to generate this new isotope for cancer treatment called actinium-225. And that's what this study from 2016 used. So there's this, ability to get larger amounts of this material and put it into the world to treat cancer. And the TerraPower engineers figured out how to extract that actinium-225 in very large amounts over time. So now we're working and focusing on that material, and it's actually happening now. So we are right now sending actinium-225. We do batches every week, and we send them to various drug manufacturers. And in a very short time frame, they'll start going through drug trials to actually get approved to treat cancer. And what they're telling us is that our research grade actinium-225 is one of the purest forms of it they've ever seen. And when we say pure, we mean that means it can go into a patient and actually treat the cancer and then leave the patient. Whereas if it comes with a lot of impurities, they tend to hang out in the human body. And so that's something you don't want. And so it's a purer form of the isotope, and it's more quantity of the isotope than you can get through any other means. So it's a really big opportunity that we're focusing on right now.
That is really cool. What a great side hustle, if you will,
yeah.
in a very, very cool and impactful way to not only you keeping the lights on, right, but you're saving lives. That's a great story. So what's next for TerraPower?
Well, yeah, I mean, we have really seeing strong demand in the market for all three programs, the Natrium, molten salt reactor, and the TerraPower isotopes. And really the message we feel every day is that we're not moving fast enough for the demand. So I think that's a good problem to have, but we really have to execute our demonstration projects, continue the actinium production on schedule. And then I think the market is ours to lose. So, I would say that TerraPower isotopes is happening now. That's like the present. I mean, material is leaving, being produced. It's really nice for those of us working on the nuclear power plant design side, because the time frame for deployment of a nuclear plant is much longer than producing a medical isotope. So we get to see some product, developing. There are also future isotopes that we could work on as well. So actinium-225 is the one today, but there's other ones that are out there being looked at as well. And if one of those shows good promise, we could pivot our, team to working on a different isotope in the future. And then we're looking for commercial units to come off of the demonstration of Natrium in Wyoming. So there's a lot of people, the growth of data centers and the use of AI has just created this enormous demand for electricity that we're hearing loud and clear. And so that's driving a lot of us to look at deploying plants, very quickly and trying to ramp up that production to, say 5 plants a year. And that may not sound like a lot, but 5 nuclear power plants a year is actually a tremendous change from where we have been in this country. So a lot of things have to happen to be able to do that. And so that's what we're looking at. And then longer term out, the path for Natrium is to actually do further advancements in fuel so that you can get to a plant that doesn't require any of this enrichment and can be deployed all over the world and start to go international with it. So in a nutshell, that's kind of what the future looks like.
Do you see an opportunity then for, let's call it data centers or other large industrial consumers of electricity, just to contract directly with you as opposed to going through, say, a utility or something like that? It's have an Amazon, a Google, or I should say Microsoft, right? That's your boss's former company kind of thing, or day-to-day job.
Yeah.
He just said, you know what, we're going to put up Azure data centers or something like that. Let's just go drop one of these reactors there because, we do a lot of work in the data centers and we see they're 300 megawatts. Some are approaching the gigawatt size now. So it's like, man, why go through the middleman? Why not just put these in when we're building the computer side of it, let's build the electricity generation side of it too.
Yeah, I think that's a good question. I do see the opportunity to actually partner with the data center to just deliver the electricity, behind the meter, so to speak, directly to them. Reliability is such a huge requirement for the data center that, that could really address that. Our energy storage capability can actually be used to provide backup to them as well. So maybe they don't need as many diesel generators to back up the data center. There's lots of interesting architectures you could think about, applying the nuclear energy, the data, the thermal energy storage along with the data center. But another thing we see is that data centers don't necessarily benefit from load following, but the grid does. And we're seeing a lot of interesting conversations when we sit in a room with the data center, plus the electric utility, plus the developer, us. And we see that conversation being very healthy, where the utility is getting a lot out of having the energy storage. The data center is getting a lot out of having the dedicated, firm nuclear asset. And we're getting a lot out of being able to serve both of those. And so that three-way deployment seems like a really healthy one to me. But I do also see the need to just deploy, in some places, it's just about supplying the power as reliably as possible to that, big consumer. So
yeah, that could be an interesting business model for those large energy consumers putting a reactor in their backyard, because they get the reliable energy they need. If they have excess, they could probably sell it back to the utility. Utilities already are looking to buy contracts for green energy, right? So it's kind of almost the perfect match, if you will.
Yeah, exactly. But the utilities, have a problem when the big data center wants to come onto the grid that they already have. So there's a problem of, adding these new data centers to existing grids. So, there is this drive to maybe look for other solutions that don't involve that. And I think that's where your point comes in.
Yeah, it's interesting. I've worked with a lot of utilities with the large integration of data centers and all the, let's call them, unique challenges that occur when you're trying to integrate those really big loads that can step on and step off the grid really quickly.
Oh, yeah.
Eric, thank you so much for your time. This has been a great conversation. If you're ever over on the east side of the state, please come by and say hello to us. I'd love to show you around our facility and show you what we do on a daily basis.
Oh, that'd be wonderful. And same to you. If you're ever out here, we have a lab here in Everett, Washington, and let me know and we'll give you a tour and let you see some sodium up close and personal.
I'm going to take you up on that offer. Again, thank you very much. And you know what? I bet we have a follow-up podcast if you're willing.
Yeah, that sounds great.
All right. Thanks, Eric.
Thank you.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.